We are going to talk about critical numbers in function analysis in calculus. Let's consider the graph of this function that we were looking at when we were discussing the basics of reading a graph. Let's review that. How many relative maximums does f have on the closed interval? I put dots on the ends of this. On the closed interval a to b, how many relative maximums does f have? Well, I view 1, 2, 3, 4. I view 4 of them. How many relative minimums does f have on the same interval? I see 1, 2, 3, 4, and 5. There are 5 of those. What can you say about the derivative of f at each location of one of these relative extremum values? Okay, remember that the derivative of f is the slope of the tangent line to the graph of this. So what can you say about the slope of the tangent line? What can you say about the tangent lines at each of these values, at each of these local extrema? Well, at each of these, the tangent lines are horizontal. At each of these, those tangent lines are always horizontal. That means that the slope of the tangent lines, the derivative, is 0 there. So at each of these, the derivative is 0. What about at this one, though? Is the derivative 0 there? No, that's a corner. So the derivative is undefined there. So at each location of a relative extremum, f prime is either 0 or undefined. And that is exactly what a critical number is. A critical number is a possible relative extrema. Okay? So f prime is either 0 or undefined. A critical number is the function f are all the values of x at which f prime equals 0 or f prime is undefined. That is the definition of a critical number. These are all the candidates for locations of relative extrema. All right, let's take a look at some examples here. So we're going to start with find all the critical numbers of this function. So I know when I see critical numbers, I think that's where the derivative is 0 or undefined. Okay, so let's go ahead and take the derivative here. So our function is g, so g prime will be, all right, I need to use the quotient rule because I'm looking at a quotient. I start up on top and take the derivative. The derivative of x squared is 2x multiplied by the denominator left alone. Minus is in the quotient rule. The derivative of the bottom is also 2x multiplied by the top left alone, all divided by the denominator left alone but squared. All right, the first thing I do is I note that we do have a denominator. That's what could make our derivative undefined. Is there a value of x that makes the denominator 0? So that's the first thing I do. If I have a denominator, I take care of that first. Let's go off to the side here. What value of x makes that 0? Well, there are 2 of them. X is equal to positive or negative 3. Those both make the denominator 0, so those are both critical numbers. Okay, now I go and look at the top, because whatever makes the top 0 will also make me have a critical number, because that will be where my derivative is 0. So now I go and look at the numerator. So I have a couple different ways I could do this. I think, well, I'm just going to write it down for right now. 2x times x squared minus 9 minus 2x times x squared. I'm going to set that equal to 0. Okay, I notice that I have a 2x in common in these two factors. So I am going to factor out a 2x. I'm left with x squared minus 9 from that term, and I'm left with a negative x squared from that term. And that worked out really nicely because my x squareds here cancel out. I have negative 9 times 2x, that's negative 18x, is equal to 0, so x must be 0. So I have three critical numbers. My critical numbers are x is equal to 0, 3, and negative 3. Those are my critical numbers. Okay, next example. Find all the critical numbers of this function. Now in this one they gave me an interval. Oftentimes when we have a trig function involved, we're going to get an interval. Otherwise we would be dealing with an infinite domain. All right. On the above one, they did not need to give me an interval. Okay. Find all the critical numbers. So critical numbers, again, I will be making note of this. Critical numbers are when the derivative, in this case the function is h, so I'm just going to go ahead and call it h, when h prime is 0 or h prime is undefined. So we're going to find h prime and then find the values of x that make it undefined or 0. So for this h, I have a product, so I need to use the product rule. I'm going to start with the first function and take the derivative. The derivative of e to the x is e to the x. Multiply by sine x left alone, plus the derivative of sine x is cosine x, multiplied by e to the x left alone. There is no denominator. These trig functions do not have any asymptotes, right? So this is never undefined. This derivative is never undefined. So we're not going to have critical numbers that come from something that make the denominator undefined. Instead, I'm just going to set this equal to 0 and solve it for x. So again, I notice I have something in common. I have e to the x in common, so I'm going to factor it out. I have e to the x outside, and from the first term we have a sine x, from the second term we have a cosine x. So I have two things being multiplied together to get 0, so either e to the x is 0 or sine x plus cosine x is 0. Well, can any x value make e to the x 0? No. There's no x value from this piece. So no critical number will come from that piece. Remember, the graph of e to the x is never 0. It's never 0. It's always positive. Always positive. Okay, sine x plus cosine x is 0. I guess I could take cosine x to the other side. So let's think about this. What angle makes sine of that angle equal negative cosine of that angle? Well, they're identical at the pi over 4s, right? They're opposites at the pi over 4s in certain quadrants. All students take calculus, so they are opposites in quadrants 2 and 4, so it'll be the pi over 4 angle in quadrant 2 and in 4, so x is 3 pi over 4 and 7 pi over 4. And those are our critical numbers. So that is critical numbers.